Hello, in this video we're going to go over convergence sequences. So in some textbooks, when they are dealing with advanced calculus or single variable advanced calculus, they start with continuous functions and they deal with functions in terms of epsilon delta definition of continuity, and then at some point they also get to the sequences and they deal with sequences and series at a later point. In our textbook, though, they talk about convergent sequences first, and this is a very interesting approach since it makes the logical argument of a continuous function easier. So the dealing with epsilon delta is a little bit more complicated than dealing with the convergence of a sequence. And I would, in fact, I actually do prefer this method. So first, what is a sequence? So a sequence is a list of numbers, and we index them by natural numbers. So a1, a2, a3, and so on. Every one of these is called a term. So an is called the nth term of the sequence. So this is something you have seen in pre-calculus. Some examples of sequences are sequence of positive odd integers, 1, 3, 5, and so on. So the nth term of the sequence would be 2n minus 1. So the first term is 2 times 1 minus 1. The second term is 2 times 2 minus 1. Any geometric sequence that you take is also a sequence, and the nth term is the first term times the common ratio to the power of n minus 1. So the first term is a times r to the power of 0. The second term is a times r to the power of 1, and so on. Any arithmetic sequence is of course also a sequence, and the nth term is the first term plus n minus 1 times common difference. And if you take a sequence an, the sequence of its partial sums is itself a sequence. So if you take a sequence an, the sequence a1, a1 plus a2, a1 plus a2 plus a3, and so on, that is a sequence. Okay, so now that we understand what a sequence is, we are going to talk about convergent sequences. What does it mean that a sequence approaches a real number? So we say a sequence an converges to a real number a, written as limit of an is equal to a as n approaches infinity, or the other way of writing it down would be an and then arrow a. That also means an approaches a as n approaches infinity, if the following holds. So I will read this statement and then we'll talk about intuitively what it means. So for every epsilon positive, there is a natural number n that after that point, so starting from a capital N and then a capital N plus 1 and so on, the difference between an and a is less than epsilon. So what does that mean? So we say a sequence an approaches a if whenever you take the interval from a plus minus epsilon to a plus epsilon, all of the terms of the sequence are in here except for finitely many that are outside. So here you could have finitely many. So a1, a2, maybe a3 is here, maybe a4 is here, and eventually you get to a capital N. But the key here is you have finitely many of the terms here. So we cannot have outside of that interval, we cannot have infinitely many elements of the sequence. So that's when we say the sequence approaches a. If no such real number a exists, then we say an diverges. There are two different kinds of divergent sequences. One kind is that when the sequence diverges because it blows up, it goes to either infinity or negative infinity, and the other one is that it is chaotic. So we will do examples of both of them. So the first one is stated in definition 2.3. Even though this sequence that I'm going to talk about diverges, but it diverges in an interesting type of way. In other words, the sequence goes to infinity. So we say a sequence an diverges to infinity, written as limit of an as n approaches infinity is infinity, or an approaches infinity, an arrow infinity, if the following holds. For every m that we take, for every positive real number that we take, after some point an plus 1, and it could be that an plus 2 is here, but after that point all of the elements of the sequence are going to be outside of that range a. In other words, larger than m, larger than m. We say an approaches infinity, and this should hold for every m, every capital M. Similarly, we say an diverges to negative infinity. So if you say it diverges to negative infinity, it means if you take an m that is negative, then every term of the sequence except for finitely many is less than m. So all of the terms are less than m. Okay, so next example, in this next example, we'll deal with some examples of limits and sequences, limits of sequences. Okay, so using the definition of limit, find the limit of each of the following sequences. So the first thing we need to do in order to be able to find the limit is to guess what the limit is. And this is something that you can do by using your intuition that you have built in single variable calculus. So let's start from part A. 1 over n. So what is the limit of 1 over n? So if you look at the sequence, it's 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. As you see, it converges to 0. So it goes to 0. So let's see what we need to prove. So let's look at the definition of the limits, the definition of converging to A. For every epsilon positive, there is an n that for every n after that point greater than or equal to n, an minus a is less than epsilon, in absolute value. So I would have to start with an arbitrary epsilon. So this is the first step. So let epsilon be positive. That's the first step of every proof of definition, showing that the limit of a sequence is a particular number using the definition. So we start with let epsilon be positive. So now let's see what we are trying to get to. So objective is this. Objective is to show that an minus 0 is less than epsilon. Now an is given as 1 over n, so it's 1 over n less than epsilon. So this is what we want to get to for all n, starting from capital N. Now if you think about this one, this is something we have talked about earlier. If you think about that for a moment, you'll realize this is exactly the Archimedean property. So now we can turn that into a regress proof. So by the Archimedean property, there is a natural number. There's a natural number n such that 1 over n is less than epsilon. Now, if n is greater than or equal to n, then absolute value of an, in this case it is 1 over n, minus 0, which is 1 over n, is less than or equal to 1 over capital N. And the reason is lowercase n is greater than or equal to capital N. If you take the reciprocal of both sides, you get 1 over lowercase n is less than or equal to 1 over capital N. And this is less than epsilon. So therefore, by definition, 1 over n converges to 0. That's by definition. Definition tells you sequence minus a in absolute value is less than epsilon after some point. Okay, so we're going to move on to the second part of this example, so part B. Okay, before we can prove the theorem is equal, the limit is equal to a given number that we think it is, we have to find it. So before we can actually say this is the limit, we have to find out what it is. Now, again, using what you have learned in single variable calculus, n squared minus 2n over n squared plus 1, I believe that's what it was, yeah. So we want to see what that is. In single variable calculus, you have learned that quadratics grow faster than linear. So in other words, the numerator has the dominant term of n squared, and the denominator has also the dominant term of n squared, which means this limit is going to be 1. But this was something that you have learned, but we're going to actually prove that in fact this is valid. So now, again, we have to start with let epsilon be positive. That would be the first step. Now, what are we trying to do? We are trying to show that the difference between the sequence and the limit is less than epsilon. So this is what we are trying to do. So we're going to work out the work it out on the right, and then we're going to write down the solution on the left. So we're going to take the common denominator. We get negative 2n, n squared minus 2n minus n squared minus 1 over n squared plus 1. And this is less than epsilon. So this is what we want to get. This is the objective. So we're going to simplify this. We get 2n plus 1 over n squared plus 1 is less than epsilon. So this is what we want to get to. We want to find some n that satisfies this. So now, how do we do that? There are multiple ways of doing that, but you have to be very comfortable dealing with inequalities. One thing you could do is you could safely drop the 1 at the bottom. This is less than 2n plus 1 over n squared. And the reason I do that is that I want to simplify this. I cannot drop the 1 on top. However, what I can do is I can replace 1 with, say, n. So this becomes 3n over n squared. And then I'm going to make sure that this is less than epsilon. So this becomes 3 over n less than epsilon. So if I take my n in a way that this inequality holds, then I would be done. And again, this can be written as 1 over n less than epsilon over 3, which is again another instance of the Archimedean property. So this is going to be my work on the side, which is not part of the proof. So we're going to work on that, and I'm going to write that down in black. So on the left, I'm going to write down the actual proof. By the Archimedean property, there is some natural number n such that 1 over n is less than epsilon over 3. Now, suppose n is a natural number with n greater than or equal to n. We're going to take the absolute value of the difference between this sequence and 1. Take the common denominator, we get 2n plus 1 over n squared plus 1. That's just a little bit of algebra, nothing surprising. So we're going to replace the numerator by 1 by n to make it larger, and we're going to drop the denominator to n squared, drop the 1 in the denominator. So this becomes 3 over n. But we know n is at least, lowercase is at least capital, lowercase n is at least capital N. So this would be less than or equal to 3 over capital N. And this is less than 3 times epsilon over 3, which is epsilon. So that means absolute value of n squared minus 2n over n squared plus 1 minus 1 is less than epsilon, which means n squared minus 2n over n squared plus 2 plus 1 approaches 1. So this completes the proof of the second part of this example. Okay, so we are done with the second part of this example. Now the third part is n squared minus 3n. We want to see what is the limit of n squared minus 3n. Again, from your experience, you know that this is a quadratic, and quadratics go to infinity as n approaches infinity. So the claim would be that limit of n squared minus 2, or was it minus 3n? Yeah, minus 3n is in fact infinity as n approaches infinity. So this is the claim. So what we want to do is we want to show, going back to the definition, this is the second definition. The definition that we have here, 2.3, which is an diverges to infinity, written as limit is equal to infinity if whenever m is positive, there is some integer that after that point the sequence is more than m. So what we want, the objective is n squared minus 3n to be more than m. Now the difficulty is the minus sign. I cannot drop that, because if I drop that I get something larger. But if you factor n, you kind of see what we need to do. Make this one large and make this one large as well. So maybe make n to be more than 1 and make n minus 1 to be more than, I'm sorry, n to be more than m, and make n minus 3 to be more than 1. So in other words, you need n to be more than m and n to be more than 4. So, and again we can guarantee that there is such an n because of the Archimedean property. Because Archimedean property tells you that every real number that you take, there is some positive integer more than that real number. So we're going to start with let m be a positive real number, and by the Archimedean property there is some natural number n such that n is larger than maximum of these two, m and 4. Now if n is greater than or equal to n, then n squared minus 4n, which is n times n minus 4, is greater than or equal to capital N times capital N minus 4, because lowercase n is greater than or equal to capital N, and n minus 4, lowercase n minus 4, is greater than or equal to capital N minus 4, and both of these two are positive. This is greater than or equal to 1, and I'm sorry, this would have to be 3, not 4. And this is going to be 1. So this is, and this is strictly more. So this is n. Thus, n squared minus 3n in fact does approach infinity. So this completes the proof of the claim. So we showed that in part C, we showed the limit is in fact infinity. And it may not be a bad idea, in fact it is a good idea to make the claim at the beginning. So maybe for all of these parts, I will write down the claim at the beginning. The claim is that limit of 1 over n is 0 as n approaches infinity. That makes things a bit more clear. And then I would put the epsilon positive at the next line, so that it's clear what we are trying to prove. And same thing for part B. I would specify, just for clarity, I would specify what the limit is. The claim is the limit of n squared minus 2n over n squared plus 1 as n approaches infinity is equal to 1. And then the rest would be the same thing. Okay, so this was the definition of limit of a sequence, and then 3 examples. All of these 3 examples were sequences that had limits. However, the first 2 examples were sequences that were convergent. This one was convergent. This one was convergent. This one was divergent. So, as I said, there are 2 different kinds of divergent. One of them is it blows up like the n squared minus 3n. The other one is something that doesn't necessarily blow up. It is kind of chaotic. So it could be oscillating. And that is the one that I'm going to look at the example 2.3. If you look at the sequence -1 to the power of n, this does not converge. Okay, so here is the solution. So think about what we are trying to prove. We are trying to prove it does not converge. So again, this is proving negatives. And proving negatives is often done by proof by contradiction. So suppose on the contrary, -1 to the power of n approaches some a. If that were the case, then what would be the problem? Again, we're going to look at the problem that might occur, and then we're going to see what we can do to disprove this. So the terms of the sequence -1 to the power of n are just 1 and -1, and you cannot avoid either of them because it starts from -1, then 1, then -1, then 1, then -1, then 1, then -1. You're always going to have both 1 and -1, which means there's not going to be a limit because the limit must be close to both 1 and close to -1. So the problem is that if you take a, it cannot be both close to 1 and close to -1. So what you want to take is you want to take your epsilon in a way that when you take the epsilon and epsilon, it is less than 2. So you want 2 epsilon to be less than 2. Then you would end up getting a contradiction. So in other words, you want to take epsilon to be less than or even equal to 2 would be fine. If you take your epsilon to be, say, 1, you would have a problem, or 1/2, or something less than or equal to 1. So, and I'm going to do exactly that. So let epsilon be 1 in the definition of limit. So epsilon equals 1 in the definition of limit tells you there is a natural number n such that if n is greater than or equal to n, then -1 to the power of n minus a is less than epsilon. In this case, epsilon is 1. So choose an even number that is more than n. For n equals 2n, we get absolute value of 1 minus a is less than 1. And let me write down the same thing for n equals 2n plus 1. We obtain minus 1 minus a is less than 1, which gives us absolute value of 1 plus a is less than 1. Now, we would have to show these two contradict each other. There are a couple different ways of showing that. One way would be to add the two up. If you take these two, add the two up, we get 1 minus a plus 1 plus a is less than 2. Now, by triangular inequality, absolute value of 1 minus a plus absolute value of 1 plus a is at least absolute value of their sum, which is 2. And this gives a contradiction. That tells us 2 is less than 2, a contradiction. And that tells us -1 to the power of n diverges. But it diverges in a different kind of way. It doesn't diverge to infinity or negative infinity because, as you know, -1 to the power of n is bounded. It doesn't really go to infinity or negative infinity. However, it does diverge.